Okay, what we have here is I'm going to create a little short little video, or hopefully a short little video, of different things that you need to do, and hopefully this will help you finish up your take-home test on Chapter 7-6. And there's 6 on there, but Chapter 7. All right, the first thing you need to know is that all these problems are going to be using U substitution. There is no parts. All right, no parts. So if you are using parts, and that means magic 7, you cannot do it, don't do it. Bad, 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 bad. All right, all these are U substitution. Now, in solving this, going through 1 and 2 and 3, all right, I believe are pretty easy and you should know how to do. Number 4, a lot of times students don't know how to do this one because it's saying, well, what am I going to use for U substitution? The first thing you want to do right here is you want to factor and use algebra. Okay, what I mean by that, all right, is that you want to take this expression, e to the 2x plus 2, and you want to multiply that by e to the 2x plus 2. All right. When you have that, is that you have e to the 2x times e to the 2x, which actually gives you e to the 2x squared. All right. And you distribute that through. Essentially, you're adding exponents, right? E to the 2x times e to the 2x would be e to the 4x, right? Right here, you have plus 4 e to the 2x. And the last portion, you'll have 4. All right. That right there, I think you should be able to solve from there. Okay. So algebra factoring. The next part right here, this one hopefully going to use factor out in this case because you want to get this to be 16. This is where you have an inverse trig or inverse tangent actually. All right. Factor out 1/16. When you have this one right here, when you factor this one out, all right, you're going to have 1/16 out here. You have dx, and you have 1 plus 9 over 16 x squared right there. You have to take this and simplify it, so you have 1/16, and you have dx over 1 plus 3/4 of an x, and all that's going to be squared. Okay, so try that one out. You should be able to do it. That's all right. Do substitution on this one. Look for the parentheses. All right. Figure that one out. Now, number 7, this is a little trickier. Okay. And when you have number 7, we have this in here. Now, using U sub, a lot of people say, well, I'm going to use X. That doesn't help me out. Well, this is where you're going to use algebra, like we did in the previous one. Algebra is a king. And what we're going to do is we're actually going to divide here into here. Okay. We're going to use long division. Okay, long division or synthetic division. I'm going to use long division. All right, figure this one out. So I'm going to divide this in here to simplify it. Okay, we're going to use algebra to simplify. So whenever you have a problem where the power in the numerator is greater than the power in the denominator, long division, we're going to divide that out. So to divide this, to simplify it, all right, we're going to take x plus 3, divide 3x squared minus 4x plus 5. All right, we're going to divide that through. We're going to have here, we have 3x, correct? 3x squared plus 9x. Make sure that we distribute the negatives through. So this is just a review of the algebra skills that you need to know how to do. All right. This will cancel out. And then we're left with is negative 13x, right? Negative 13x. Next part is, we'll get this negative 13x, negative 13. Okay, through negative 13x. It's going to give us negative, oh, bring down 5. Negative 13x is going to be negative 39. Right here, change opposite, opposite. All right. And so what happens is this will cancel out. And then we're left with is 44. All right, as our answer, and that's our remainder. One thing we do then is that now we have this, we're going to write this back together, all right, because we can write this expression now as, this is our quotient. This is what's known as a divisor. This is our remainder. And we can then take our quotient, which is 3x minus 13, and we're going to add our remainder, which is 44, and divide it by our divisor. And that's how we do long division, because if we have like 5, then we have a 3 here, it'd be 5 and 3, whatever that may be. All right, and then we have that right there. Now from here, now we're going to take this and we're going to use, all right, our integration to solve that problem right there. Okay, hopefully that helps you out, but long division, that's the key for that one. Okay. From here, that one's pretty easy substitution. This one, make sure you write it as the integral. All right, this is just going to be u substitution. We have 4x minus 3. All right, the 1/2 power. All right, u substitution for that one. U substitution for this one, it works out pretty nice. All right, this one we have to show, doesn't appear there's going to be u substitution, but we have that. Definitely u substitution here. These are extra credit, which I'm not going to show you because that's extra credit you should know how to do. Okay, so we have that. All right, so hopefully this helps you out to solving these exponential ones. I'm going to move on. If you have any question on these, we are to solve the differential equation. What does that mean? That means we need to separate variables and solve for x. So for example, when we have this, I'll just go through a couple. All right, I'm going to solve dy dx. That means I'm going to have dy equals negative, oh, I'm going to put the y on the other side. All right, for the y's and all the x's on the other side together. And so we have then is dy over y squared. I'm just going to keep the negative on the other side. Negative dx. You could bring the negative on the other side, but it's a little bit nicer. Right here, and now we're solving this. We're going to integrate both sides. All right, put this up on top. All right, y to the negative second dy, and that equals negative dx. All right, and you integrate that. You have your c, you plug in your initial condition. Here's your x, this is your y value. All right, to find your c value, and we go from there. Remember, y prime equals dy dx, so we have that right there. Okay, separate variables, simplify, get all x's on the other side, so and y prime should equal 3x squared. All right, solve that way. Same thing here, you gotta get everything on one side. We do not have an initial condition in this one, so we just have a plus c. Here we do have, once again, another initial condition. Solve for y prime, and then solve going from there. For our velocity functions, remember, the derivative of our position, s, all right? So if we have s as a position, I'll review. S prime is velocity. S double prime is acceleration. All right. Acceleration. So if we take the integral of s double prime, all right, we get velocity. Take the integral of velocity, we get, all right, position. We're asked to find, all right, v of t and s of t. Each time you do that, and we're given a of t, all right, our acceleration. We're given initial conditions for each one. This should be an s value there, not x, but that's what we have there. X or s is the same thing, so we're going through the same way. Make sure you plug for each one the initial condition to solve for your values. From here, this is what we have. This should be a p right there. I said that before. But a long-term ecology study found the population of trees in the forest is growing at a rate proportional to the number of trees presented in this very differential equation. All right. If there were 100 or 600 trees when the survey started, and there were 8,300 trees in 6 years, all right, find the equation that used to predict the number of trees. Now, we talked about this the other day. I'm going to let you figure that out, but I will tell you there are some points. If there are 600 trees when the survey first started, so that when t equals 0, the population of trees, p equals 6,000. When 6 years later, when t equals 6, the population of trees was 8,300. All right, we want to find the equation for this. A little hint, when you find this equation, you need to find, all right, the k value as well. Okay, you need to find the k value. All right, when you solve this initial condition, all right, we went through this, and we know that dp dt equals k times p. All right, separation of variables, dp over p equals k times dt. All right, k is a constant of proportionality. That is our constant. That is not a variable. T is our variable, and p is our variable. So we need to integrate this. We also have our notes a fast, efficient way of doing that. Okay, I'm going to let you figure that out and do the algebra going from there. Over here, though, all right, I am going to go through and talk about this, all right, problem. All right. When we have this, all right, I will show you because a lot of students have questions on how to figure this out. So 23, I will go through, all right, this one, all right, that one, and I'm going to let you solve the bottom three, okay, on your own. But, so here we go. First off, write down a differential equation. The differential equation is the rate at which the number of bears, n, in the population, all right, so the rate. So we know dn dt should equal is directly proportional. So directly proportional means we're going to have some sort of constant proportionality to this value, all right, right here. So we have 1200 minus n, and that's what it means. So the rate, the ndt, in the population is directly proportional to 1200 minus n. 1200 minus n. All right, where t is greater than or equal to 0. If the time in years and k is a constant proportionality, which we know, when t equals 0, the population is 300. Okay, so that's our initial condition. All right, and we have this. Now, unlike our previous problem, this is not just simply an exponential, regular exponential one. Okay, we actually have to solve this. So this is our differential equation. That's it. dn dt, which is our differential, is equal to k times that, because that's what it says it is. It's directly proportional to this equation. We now want to find what n of t is. So that means we want to solve this differential equation. All right, we want to solve the differential equation. All right, which is a lot of fun. So in order to solve the differential equation, all right, I'm going to change my color here. I'm going to go to black. All right, is that we're going to separate variables. All right, so it's going to be 1200 minus n. This is one expression. It has to stick together. Expressions stick together. All right, so we have dn over 1200 minus n. Okay, and that's going to equal k dt. All right, from here, we're going to integrate this, both sides. Now, this is right to n. If you look at this, this is a power of 1. This is our y value, or our output, right, our dependent variable. So when we integrate this, we know it's going to be the natural log of the problem, 1200, minus n. Now, if you recall, divided by whatever the coefficient is here, so divided by -1. Okay? We could use substitution with this one as well, but this is the fast, efficient way of doing it. Okay? On this back side, we have kt plus c. All right? Kt plus c. Now, from here, all right, I want to find this in terms of nt. So from this point, we can simplify this a little bit. So we have negative natural log of 1200 minus n. All right, and then we have kt plus c. And so we are now going to plug in our initial condition. We have to solve for c, and we are given an initial condition. We're given this value right here. Whoop. All right, so we're going to take that and plug it in. So when t equals 0, that's 0, n equals 300, so we're going to plug that in there. So we should have negative natural log of, plug that in there, would be 900 equals c, right? So we have our c value. We'll continue on. And so we have negative natural log of 1200 minus n. We'll have kt. We'll have minus natural log of 900. All right. And now we're going to solve for n. And we're going to keep this in terms of k, nt. So first off, we're going to divide by negative. We have natural log of 1200 minus n equals negative kt. And that's going to be plus natural log of 900. From here, we're going to e both sides to get rid of that, right? Because these will cancel out because they're inverse operations of each other, so cancel out. We're left with 1200 minus n. And that's going to equal e to negative kt plus natural log of 900. Now, when we have this, whenever we have a plus sign here, we know we can write this as negative e to the kt times e to the natural log of 900. These are inverse operation of each other. These cancel out. We have 900 e to the negative kt power. That equals 1200 minus n. All right. From here, we're going to subtract and then divide by negative. So we're going to have n, our final thing, 900 e to the negative kt. It's going to be minus 1200. We then divide by the negative, so it's going to turn negative. That's going to be positive, and that's going to be our solution of our differential equation. All right. From here, this is a k, this is a t. We can use that to solve our remaining ones. So now this is just algebra. Plug in that point to solve for k. Calculate when we do that, and what is n equaling 8? So that is going to be when n in 8 years. All right, from its initial position. What's the total number of bears that we're looking for? And what happens when n goes to infinity? Okay, what happens when n goes to infinity? All right, what happens? Not when n goes to infinity. I'm sorry. When t goes to infinity. When t goes to infinity, how does that solve? Okay. All right. Well, that's that one. I think that should be able to help you out. And then one more thing. All right. The half-life of radium is this. So how do you set this up? If 1,200 grams are present in a sample, how many grams would be there? All right. Whenever you have half-lives, all right, into the problems, this is the PERT formula. All right. So our amount is equal to our initial amount, e to the kt power. What we know right here is we're going to plug in our value. So if we're present in the sample in 1,000 years, how many would be in 1,000 years later? We're going to just say, all right, this is 1,000 years. We're going to say that's going to equal 0. So essentially, this is going to be when t equals 1,000. All right, we have that. So our initial amount, the amount of, all right, radium we have is going to be 100 when first 1,000 years when t goes in. We know the half-life. Okay, so whatever it is, the half-life of that, all right, so the half of this amount is going to be that. So when t equals 16,020, all right, or 1,620 years, we know our amount is going to equal 1/2, which would be 50. Erase this and move it over. All right, and so that's going to equal 50 grams of radium. And then we're trying to figure out how much is left after 1,000 years. Okay, so we have 2 points. We have this point right here, and we have this point right there. Okay, and so what we have to do is figure out our initial amount, which is 100. We can figure out our k amount, all right, by using our other point. So if we plug in our other point right here, we'll have 20 equals 50, and we have to solve for k. All right, I'll let you solve for k. After you solve for k, plug it back into the equation, and then you want to figure out and plug in t, and then pick your answer for the number of grams. Okay, the rest of the problems I think you can figure out there. Review, you can look at them up and whatnot, but hopefully going through all these different problems helps you out, able to go through, just like being in class. All right, and yeah, you should be able to finish up the rest of this sheet for whenever we meet next. Okay, well, good luck and God bless. If you have any other questions, please email me, and we'll talk to you later. All right, bye.